Algebra by Michael Artin. Chapter 2, Groups. Section 4, Homomorphisms. Let G and G' be groups. A homomorphism, phi mapping G to G', is any map satisfying the rule 4.1, phi of AB is equal to phi of A times phi of B, for all A and B a member of G. This is the same requirement as for an isomorphism, see 3.2. The difference is that phi is not assumed to be bijective here. 4.2 Examples. The following maps are homomorphisms. A. The determinant function. The determinant GLN of R maps to R star. B. The sign of a permutation, sign S of n mapping to plus or minus 1. See Chapter 1, 4.9. C. The map phi mapping the positive integers to G defined by phi of n equal a to the n power, where a is a fixed element of G. D. The inclusion map I mapping H to G of a subgroup H into a group G, defined by I of x equal x. 4.3 Proposition. A group homomorphism phi mapping G to G' carries the identity to the identity and inverses to inverses. In other words, phi maps the identity of G to the identity of G', and phi of A inverse is equal to phi of A inverse. Proof. Since 1 is equal to 1 times 1, and since phi is a homomorphism, phi of 1 is equal to phi of 1 times 1, equals phi of 1 times phi of 1. Cancel phi of 1 from both sides by 1.12. 1 equal phi of 1. Next, phi of A inverse times phi of A is equal to phi of A inverse A is equal to phi of 1 is equal to 1, and similarly, phi of A times phi of A inverse is equal to 1. Hence, phi of A inverse is equal to phi of A inverse. Every group homomorphism phi determines two important subgroups, its image and its kernel. The image of a homomorphism phi from G to G' is easy to understand. It is the image of the map. 4.4. The image of phi equals the set X a member of G' such that X is equal to phi of A for some A a member of G, and it is a subgroup of G'. Another notation for the image is phi of G. In examples 4.2 A and B, the image is equal to the range of the map, but in example 4.2 C, it is the cyclic subgroup of G generated by A, and in example 4.2 D, it is the subgroup H. The kernel of phi is more subtle. It is the set of elements of G which are mapped to the identity in G'. 4.5. The kernel of phi is equal to the set A a member of G such that phi of A is equal to 1, which can also be described as the inverse image phi inverse of 1 of the identity element. See Appendix 1.5. The kernel is a subgroup of G because if A and B are in the kernel of phi, then phi of AB is equal to phi of A times phi of B is equal to 1 times 1 equals 1. Hence AB is a member of the kernel of phi, and so on. The kernel of the determinant homomorphism is the subgroup of matrices whose determinant is 1. This subgroup is called the special linear group and is denoted by SLNR. 4.6. SLNR equal the set of real n by n matrices A such that the determinant of A is equal to 1, a subgroup of GLN of R. The kernel of the sign homomorphism in example 4.2b above is called the alternating group and is denoted by A sub n. 4.7. AN equal the set of even permutations, a subgroup of Sn. The kernel of the homomorphism 4.2d is the set of integers n such that A to the n power equals 1. That this is a subgroup of Z+ was proved before in 2.8. In addition to being a subgroup, the kernel of a homomorphism has an extra property, which is subtle but very important. Namely, if A is in the kernel of phi and B is an element of the group G, then the conjugate BAB inverse is in the kernel of phi. For to say that A is a member of the kernel of phi means that phi of A is equal to 1. then phi of B inverse is equal to phi of B times phi of A times phi of B inverse is equal to phi of B times 1 times phi of B inverse, which is equal to 1. So B inverse is a member of the kernel of phi 2. 4.8. Definition. A subgroup N of a group G is called a normal subgroup if it has the following property. For every A a member of N and every B a member of G, the conjugate BAB inverse is in N. As we have just seen, 4.9, the kernel of a homomorphism is a normal subgroup. Thus, SLN of R is a normal subgroup of GLN of R, and AN is a normal subgroup of SN. Any subgroup of an abelian group G is normal, because when G is abelian, BAB inverse is equal to A. But subgroups need not be normal in non-abelian groups. For example, group T of invertible upper triangular matrices is not a normal subgroup of GL2R. For let A equal the matrix 1, 1, 0, 1 and B equal 0, 1, 1, 0, then BAB inverse is equal to 1, 0, 1, 1. Here, A is a member of T and B is a member of GL2 of R, but BAB inverse is not a member of T. The center of a group G, sometimes denoted by Z or Z of G, is the set of elements which commute with every element of G. 4.10. Z is equal to the set Z a member of G such that Zx is equal to Xz for all X a member of G. The center of any group is a normal subgroup of the group. For example, it can be shown that the center of GLN of R is the group of scalar matrices, that is, those of the form Ci. Algebra by Michael Artin, MIT. This book was published in 1991 by Prentice Hall. It is read by Jim Renhold, with programming and illustration by Jim Renhold, 2019. Thank you for listening.